chapter 8, okay, what we have discussed together is, you guys ready? Are you guys ready?
Tolong jangan buat aku koyak tu. Kasi mana dia buat
Excuse
nak
me,
buat
your mic. Okay. All right. So previously we have done until this part where actually this is where we stop related to the rotational motion or rotational kinematics. So just to share with you what we have in rotational kinematics is related to all motion, okay, only motion. So in the motion that we have, okay, let me just get back to, okay, this one. Okay, so in the motion we have, it's related to all displacement, velocity, and acceleration. So I think I have um, shared with you, and I asked you to do a little bit summary on what we have done in the earlier part of chapter 8, where you can use this slide for the guide. For the displacement, velocity, and acceleration, previously we use as S, V, and A. Instead of S, you also can use X for horizontal displacement and Y for vertical displacement or height. And then these are the equation that we have we have discussed. Okay, maybe not on A equals to R alpha. There actually, and there is another one related to that, but that one I will explain later. Okay, so basically these are the symbols we have in linear. So you just change to another symbol we have in rotational motion. So if you can use this slide to add the unit and also add the equations related. Okay, more or less for the omega, you also have two equations related to the period and also the 2 pi, okay, related to two complete rotation. And then we have acceleration as A or alpha. And then for kinematic equations, okay, you are going to have three kinematics equations that we have in linear motion. So you need to use the same equation but change to the symbols that we use in rotational motion. So basically, like I said to you in the class, whatever you learn in linear motion up until circular motion, more or less those are the thing that is related to rotational motion as well. You just change the symbols, okay, and somehow they are interrelated. So please put highlights there, okay, whenever I say okay, how things is changed from linear to rotation, then you can highlight that. That will be good, okay, when you revise later. So we stopped here the other day with example 7, okay, and I've given you the solution as well, so you can try to calculate again if you haven't. Okay, and then today I would like to quickly introduce to you components of acceleration in case we have non-uniform circular motion. So this part is actually a little bit not for rotational motion. It's a little bit related to circular motion previously. Okay, just that because I want to introduce to you these terms, tangential acceleration. Okay, why do we have this tangential acceleration? So because this tangential acceleration is what we are going to use later in the talk and related to yeah, the torque. Okay, and for the point on rotating body will experience acceleration. There are two components of acceleration. We call them as centripetal acceleration and tangential acceleration. But bear in mind, okay, for chapter 7, we normally discuss things about uniform circular motion. So uniform circular motion is where you have the speed is constant in circular motion, so you only have one type of acceleration. You call that as centripetal acceleration towards the center. But what if you have the motion that is not uniform? So for example, you have this guy, okay, and this guy is having the circular motion with the model airplane in circular motion. But let's say this guy is not stable, so he is moving left and right, back and forth while doing the circular motion. So when he is moving not at a fixed place, more or less, the acceleration is not only centripetal. This motion will have another acceleration. You call that as tangential acceleration. So this tangential acceleration, by the name itself, is always tangent to the circular path. So when it is tangent to the circular path, it is more or less like this. Okay, like occupying the y-axis, and AC somehow occupying like x-axis. So when you have one occupying x, one occupying y like this, so that means the acceleration um, is not x-axis or is not y-axis. It's somehow in the middle, comes with certain angle. So this is where you can do or use the vector knowledge for that. But if this is if we are referring to this point here, okay, this is the point where the aeroplane is located. You will see that AT is y-axis, AC in x-axis. But as it goes around, at one point later, you may find that AT becomes in x-axis, AC becomes like y-axis. So because the motion is in non-uniform circular motion, so somehow AC and AT will interchange between the axes. Okay, it can be x, it can be y at different points. So what I would like to say is that if you want to calculate for the magnitude of the acceleration, it doesn't matter if you want to put any of them as x-axis or y-axis. Okay, so just calculate with the magnitude. So I want to share with you what is AT and AC. So again, okay, this might not be in your final exam, but I really want to share with you this knowledge when we have non-uniform circular motion. So basically, for centripetal acceleration, by the name itself, it is still centripetal acceleration. It's not angular acceleration. So when you have centripetal acceleration, your symbol is AC. Based on uniform circular motion, AC is referring to the centripetal acceleration equals to V square over R. But referring to rotational motion, okay, somehow we want to have a relation between centripetal and rotational. So this is how the equation being derived. So when you have V square here, we know that V is equals to R omega. So when V equals to R omega, what you have there in the bracket, it becomes R omega square. So both must be square. One of the R will be cancelled with the one down here. Then your AC is equals to R omega square. So in rotational motion, like I said to you, while the rotational motion take part, okay, when you put an object, the object will move somehow in circular motion. So that object will have centripetal acceleration towards the axis of rotation as well. And the value is given by R omega square. Omega refers to the angular speed. And then the unit for AC is meter per second square. So be careful here. Since we define centripetal acceleration as A, not alpha, it's A. A will give you meter per second square. Okay. And then for tangential acceleration, what you will get from that, it's the rate of change of speed in the direction of the tangent to the curving path. So speed is always changing. Okay, why speed is always changing? Because the direction of velocity is always changing. So when the velocity is speed is changing because of the velocity is changing, then you will have the tangential acceleration as well. So that tangential acceleration is given by, initially the formula is V over T. Then again, we put that for rotational motion, V is equals to R omega. Then you will see that omega over T will give you alpha. Omega over T is the change of speed, angular speed over time. Then it will refers to alpha. Then AT is equals to R alpha. Again, we define this as A. So acceleration is in ms negative 2. So for non-uniform circular motion, when the motion is having changes in speed and change in direction, so that means you will have two types of acceleration. We have tangential acceleration and also centripetal acceleration. So both will occupy different dimension. One will occupy x-axis, the other one will occupy y-axis. Then together to find the total acceleration, which is right in the middle here. It's somehow in the middle, we don't know. Okay, the direction is not perfect. So centripetal acceleration. Oh yes.
I have a question. What is alpha again?
Angular acceleration.
Okay, thanks.
Okay, and AC is equals to R omega from just now, and then AT is equals to R alpha, because AT somehow in y-axis, AC somehow in x-axis. The way to get the A is basically just like how you calculate for the magnitude of vector. So AT square plus AC square in the square root. When you are using tangent, antitangent, AT over AC, so you will get that the angle is near to x-axis. Okay, so it's like that. So here the angle is written as somehow a little bit different, but you can also just write it as theta. So these are the two things, okay, two accelerations you're going to have when the motion is not uniform. Okay, so yeah, I just want you to know, okay, that you have AC and AT. So that's all for total acceleration. Okay. I don't really want to go into this part for the in deep, so you can just look at it. But again, it won't be in your final exam anyway. So I just want to introduce that to you so that you have a little bit knowledge on non-uniform circular motion. Okay, so going to the next part, we have rolling motion. So for this rolling motion, what do you have there is, like I said to you, okay, there's a difference between rotational motion and rolling motion. Rotational motion is just rotating at one place. Rolling motion, it's rotating and change position as well. So what you have there is rolling motion is rotating motion plus translating motion. So at the same time, it is rotating and it is also changing position like that. Okay, so it's moving to a certain position later like that. Okay, so for rotating plus translating, we call it as rolling motion. There is a term that you can always find this in the question, where the term is rolling without slipping. Okay, so rolling without slipping means the wheel is momentarily in contact with the ground and no sliding or skidding between the contacting surfaces of the wheels and the road. So for example, this means that the rotational motion, the rolling motion, translating motion is being done smoothly. So because you know that when the bicycle is rotating, for example, if you have a bicycle and you know how to ride a bicycle, when it is somehow rotating, there is a certain point that you will feel that somehow your bike can be like just screeching, or the tire is not properly rotating. So that will make your calculation harder. So in order to make our calculation easier, we have to think that our rolling motion is always idle, it's always perfect, it's always smooth. So rolling without slipping means that it will be in contact with the surface all the time, rotating and rolling smoothly. Okay, so please take that. And okay, for the mechanics of rolling motion, what will happen there is, as the wheel of radius r rolls, so let's say you have this wheel with this radius r, it rotates about an axle, so it is also called axis, for one revolution. So if this rotating object is rolling one whole turn within a certain time t, it is also saying that the object is moving as 2 pi r in a straight line. So as the object is rolling one whole turn, it is also said that the object has moved with certain distance equal to the arc length, or what do you call that? Circumference of the tires. And how do you see that? For example, see this carefully. Okay, see the slide carefully. Let's say I put here as 0.1. Okay, This is 0.2. This is 0.3 and another 1.4. Let's say the object is rolling like that, and this is rolling in clockwise direction. Okay, you see that it is rolling in clockwise direction. So when it is rolling in clockwise direction, okay, so let's give it a time frame there. At this point, sometime later, 0.2 will reach this point. After some time later, 0.3 will reach this point on the ground. After rotating some more, 0.4 will reach this point later, back to 0.1 here. So this means this object is already complete one whole turn, one whole rotation. So that's how you say the object, while it is rotating, it will also make this object moving with certain distance on the ground. So this is what they have in the car, in the motor, to calculate for the mileage of the car. So the mileage of the car is referring to how much the tires has rotated. So when the tires has rotated, then it will bring you to a certain distance. So that is what you call as mileage. Okay, so can you see this? Can you understand this part?
Yes, yes.
Okay, so
Yes.
this distance, okay, this distance on the ground is what you refer to as this linear distance there. Although it is rotating, it is also translating. So that's linear distance is given by L equals to R theta. Basically, this is also referred to the circumference the other day. Okay, we have S equals to R theta. So it's actually the same. Okay, and let me show you this thing. If you feel like you cannot see this much, okay, I have this from online. Okay, you can see that as the object is rotating, it covers a certain distance on the ground, and that distance is the same as the circumference of the whole rim of the tire. Okay, so basically this is the rolling motion. Okay, you need to have this equation S equals to R theta and V equals to R omega if related to angular speed and or tangential speed. So this is basically how you have your mileage in the car, and also the bigger the radius of the tire, it will bring you to more distances when you complete one rotation. Okay. All right. So okay. Let's calculate for example 9. Read the question. I also have the answer there as well. So please try to read the question and find the solution. The final answer there is 40.9 revolution. So try to calculate for this. Okay, done. Okay, so you have a bicycle rolling down a slope of a hill for a distance of 90 meters. So this is the distance covered on the surface. The diameter of each tire is 0.7. So please note this word diameter. And you are asked to calculate for revolution of the tires. So because each tire, we take that the tires are the same in front and at the back. So you want to find the revolution means you want to find the theta. But the theta is needed to calculate in revolution. So when you use the equation S equals to R theta, your theta is in radian. So make sure to convert that to revolution. So the conversion here is 1 revolution equals to 2 pi rad. Make sure to get your final answer correct as 40.9. That should be my answer at least. So if you have any other answers, please tell me.
Miss,
Uh-huh.
Can I ask about attendance real quick? My power-ups for some reason isn't working still. So you're gonna...
Nikita,
For
you need to sign out and re-sign in again.
Yeah, I know. I don't know. It's still not working.
okay, so for the attendance, if you can do the power apps, please do the power apps. But for your own for the attendance with me, I will give my form later at the end of the class. So no worries. Okay, no worries. If your attendance is not in the power apps, I do have that in your in another form. So don't worry about that.
For this chapter about bicycle rolling down the slope, right?
Mhm. Yes.
We won't like consider the friction for now.
No, we don't have. We don't consider the friction for this one because this one is not related to any force. It's just the motion itself, not force yet.
I see. Alright.
Okay. All right. So basically, your calculation will start with S equals to R theta. So know that you need to find the radius. So if you use 0.7, of course, you won't get this number. So please check that again to get the radius. And again, I said that when you use the equation for S equals to R theta, the answer that you get for the theta should be in radian. So since the question asks you how many revolution or how many times it has rotated, means you need to check that in terms of revolution. So convert that to revolution, you will have 40.9 rev. Okay,
Hi,
so
Miss.
yes.
Hello.
Mhm.
Can you explain me how to change from the radian to the revolution? I'm confused.
Okay,
Okay.
take 1257.1 radian and then divide by 2 pi, and then you get revolution.
Okay, so for example here, I write down for you as well. 2.257 radian there. Okay, and then you know that one revolution equals to 2 pi rad. So in order for you to cancel this rad, you must put the rad down here. Okay, rad. So one revolution is equals to 2 pi rad. So rad and rad be cancelled. There you go, you have 257.1 divide by 2 pi. So you will get 40.9. Do you get that?
Yes.
All right. So I think there are quite a lot of you who are still confused about the conversion. Please do more conversion. Okay, when you discuss with each other, okay, try to just randomly convert few things to another units. Okay, so that's how you can also practice on conversion. Okay.
Miss,
Yes.
do we have to use this equation?
Which one?
The S equals R.
Well,
Theta?
pilihan ni.
Do you have any other formula to find the answer?
It's not formula, it's just like logic, like, yeah, kind of logic.
Okay.
Yeah.
The thing is,
Well, physics is all about logic.
okay, the thing is, this is also logic. I don't know if any of physics formula is not logic, but for this formula, it is referring to, because when you use the correct formula in physics question, it shows that you know in the calculation all the parameters are related. So if you calculate for the theta, it is somehow the factors related to the theta is the radius and also the circumference. So that's why we need to use the formula so that you know those are the factors affecting the motion.
Oh, okay.
All
So
right.
what you-
Understand that you can actually find with other, maybe you can find with other formulas related to math or something, but if can provide the formula related to physics so that whatever happen in the future, if the questions change the parameters, you know how to work with the formula.
I see, okay.
Okay.
So if like the circumference, right? I
Uh-huh.
calculate for the tires one.
Mhm.
Is it possible?
Circumference of tires one.
I calculate for the tire and I divided by the distance. And I got the same answer. So is it possible also?
I think it should be the same actually, because it is so much related with the S is actually the circumference. So basically what you are calculating is still the same.
Right.
Okay.
Anyway.
So I think it should be logic there. It's just that you need to find the similar or common point of the calculation you make with this one. Okay, I don't want to say that the calculation is wrong. No. Okay, no such thing. But if the calculation is logic and also can be used to find the same answer, okay, by all means you can do that as well. Okay, so what I'm teaching you here is the correct way, okay, of using the formula step by step. Okay. All right. So for example 10, okay, I really want to have this as DIY, but it's okay. Let's do this together. So try to read the question carefully and find the answer. So for this answer, the question is a little bit long, but it comes with a lot of information. Okay, so when the question is longer, there will be a lot of information that you can use. So don't be afraid of long questions. Okay, so example 10, a car travels at 110 kilometers per hour. Tires of the car has a diameter of 600 millimeters. So please refers to the unit very carefully. It's not in SI unit. Determine the angular speed. In other words, you want to find omega. And in RPM, okay, this one is already been given specifically as in RPM. And the number of turns the car tires have made after travel 1 kilometers. So this is what you need to also find. The number of turns is basically the data. So try to find the answer. I'm giving you 3 minutes. Okay, read the question again, and then find out what is the answer. Okay, whether you can get this answer or not. Now let me give you the answer. Data is 5305. Okay, and omega. Okay, so omega equals to okay. Whatever you calculated, you will get in SI unit. But since the question asked you specifically to calculate in revolution and RPM, so try to do it one by one carefully. Okay, I gave the answer wrongly arranged. Supposedly you will get omega first, then you will get your data. In this question, you are not given with any. I mean, you are given with the speed, but you are not given with initial or final. So that means you just need to use the appropriate formula, okay, for you to find theta and omega. So what you have in the question is omega in kilometer per hour. So you know that this is kilometer per hour. So when it is kilometer per hour, this is basically V. So velocity in kilometer per hour is not in SI unit. So change that to meter per second. Okay, that's the way to calculate for it. And what's the equation you can use? Okay, in order for you to calculate for omega, we have the equation V equals to R omega. And to calculate for the theta, you can use the equation S equals to R theta. So please use that, and I hope you can get the final answers right. Siapa tu? Okay, so again, your V is in kilometer per hour. Change that to meter per second. That's your first step to calculate. Okay, and you should get 30.6 meter per second. You are asked to calculate for omega. Then omega requires you to have radius. Then find the radius. Omega equals to V over R. Proceed with the calculation. You should get that in radian per second because the question asks you to justify the answer in RPM, then convert to RPM. So you should get 972.6. Okay, my answer is a little bit different, but it's okay. Okay, maybe just a little bit different in decimal places is fine. And then theta equals to S over R. So this is coming from S equals to R theta. Again, when you use the equation, you will get your answer in radian. But since the question asking you to find the number of turns, you can only get the number of turns when you change everything to revolution. You change the displacement in revolution. So you will get 530.5 revolutions. Okay. So that means in 1 kilometer distance, it has rotated 530 times. Okay. All right. Any questions so far?
No, but just need like 5 minutes to process everything.
Yes. No problem. Okay.
Why 60 again for the
Why 60?
angular speed?
Why what?
Why 60 over why 60 the angular speed? You know the 101.9 multiplied by 60 over 2 pi. Why 60?
Yeah, because 1 minute 60 seconds.
Oh yeah, round per minute.
Oh God. Please check again, everyone.
Revolution per minute.
Miss.
Yes.
So, where we get the revolution, so it means that the tire has rotate 530 times.
Correct.
Okay.
Because when you see in radian is in angle. So when you see in radian and it is in angle, you don't really see how much it has rotated. So if you want to see how much rotation it has made, it must be changed into revolution.
Damn, that's a lot of turns.
Correct. Yeah, it's 1 kilometer anyway. So of course it makes it. And you can see that. Yeah, if you can see the 1 kilometer is the distance. Of course, it has rotated a lot. And you can see that the rim is 0.3 meter. It is actually for the car with rim 15. So yeah, so it's more or less it's like that. Yes.
If I had a bicycle, road bike, so like I usually like do 3 kilometers minimum, and the CC is like 700. So
CC?
How much?
What?
The circumference 700 cc. So how much round?
What is CC?
Yeah, what is CC?
CC is engine displacement. I don't see how that relates with the tire, Mirza. The heck?
CC.
But I remember they said.
I think that has nothing to do with this topic, Mirza.
Yeah.
That's horsepower related things already.
That's a power related maybe. Power related is different. Yes, question.
Why, like, you know, when after omega V O R, then at the end we get 101.9 radian per second.
Okay.
Yeah, why do we have to, what does the 60 over 2 pi is, like, what does it stand for?
Because your answer now is in radian per second. We are finding in revolution per minute. So you have to convert it. So it's second to minute, you have to times 60. Then the red, if you want to convert it to revolution, you have to divide by pi, 2 pi.
61 seconds, 61 minutes.
Miss.
Correct.
Miss.
Yes, question. Thank you for answering that question just now. It's Judah, right?
Yeah.
Okay. Yes, your question, girl.
I don't understand. The V is 110 kilometer per hour, right? What is 1000 divided by 2000?
Yeah, because it's kilometer. 1 kilometer, 1000 meters. 1 hour, 3,600 seconds. So that's how you convert kilometer per hour to meter per second.
It's not 110 times 1000?
Oh, this one is 100. Okay, please check that.
110, right?
Supposedly 110. Thank you so much for that. I think that is the number correct or the
The
number is
answer
wrong?
is correct, but it's just in a typo
Okay.
only.
All right. Thank you. Thank you.
Uh,
Thank you so much. Yes.
Kenapa 101.9? Bukan 102.
Dapat 102.
100.
Tak apa. Boleh je lebih kurang. Okay, my answer is actually 101.87. If you use your velocity is 30.56. That's how I calculated. Okay, so it's a matter of decimal places only. So I think it should be okay. All right. Okay, so for the decimal places, I think you can keep to your answers as long as it's not so much different than mine, or we can just check again. Okay, you can check with your friends just to make sure okay your calculation is right. Okay, so done with this part. Cik Firdaus, awak nak present apa? Okay, so for example 10 is done, then let's do the next part, which is rotational dynamics. So now comes the hard part. So listen here carefully, very, very carefully. I know you've been doing good job giving the focus to the class, but this one requires you to focus more, okay? Open the eyes bigger. Anyway, for the rotational dynamics right now, we want to put in the mass of the rotating object and the force of the rotating object. For example, okay, if you want to open the door, okay, opening the door is basically rotational motion. Okay, because one side of the door is fixed, the other one, okay, normal door. Okay, normal door. It's not an automated door. Okay, so the normal door, you have one side fixed, the other one is for you to freely open or close the door. So in order for you to open and close the door, you need to put some effort, okay, to open it where you need to exit the force. Okay, so let's say this is the door. Okay, this is the door and you have the doorknob at the end. Okay, this is where the doorknob is located. So if you want to open this door, becomes like the other. Okay, open. So open, make a certain angle there. Okay, so this is basically the rim of the door. Okay, this is where your doorknob. Okay, now you open the door. So when you open the door, you need to exert some force, okay, on the doorknob, whether to push or pull it. Okay, so in order for you to have the, in order for you to rotate the door, then you have to have the force there. So the force you exerted, okay, will rotate the door either clockwise or counterclockwise, either to open or to close it. So how do you know that this is a rotational motion? Okay, so you can see from the top part. So if you see from the top part, you can see that the system is somehow making either rotational motion. It's not a full rotation. Okay, it's just part of the rotation anyway. So it will make either clockwise or counterclockwise motion. Or if the door can have some mark on the floor, you will see that it makes some line like that. So this is basically refers to the axis of rotation, and you will see that it's either clockwise or counterclockwise. So whenever the force comes into picture, okay, then you will see that it is now about dynamics. Okay, it's now about dynamics. And for a rotating object, it is actually different when you try to, okay, if you have a pen in your hand, if you want to rotate the pen or pencil, it will be different if you try to rotate the calculator. Okay, so when you rotate the pen and the calculator, basically they are different shape and different mass. So those are the factors that we are going to put in the calculation, okay, and see what are the factors related to the rotational motion as well. So basically for rotational dynamics is for you to know how to rotate object, and also what direction it is rotating, and what is the factors affecting the rotational motion. Okay, so in linear motion, you have force that is contributing to the acceleration, okay, based on a certain mass. So if the mass is kept constant, if you put larger or lower force, it will affect to the acceleration, whether it is decelerating or accelerating. So in rotating object, the thing that is contributing to the force, contributing to the rotational motion, is what you call as torque. Okay, so it is given by TORQUE. The name given is torque, and the symbol is this, something like T with the tail like that. I think it is called tau. Okay, I don't know. I think it's a Greek word. Again, you can check. Okay, it is called tau, and it is a symbol given to torque. It is known as a force applied to an object to rotate it about an axis. So for the torque that you have, the torque is basically defined as how easy the object can rotate. If the torque is large, means the object is easy to rotate. If the torque is small, means the object is hard to rotate. Okay, so in order for you, I mean, it's basically subjective, depends on function, whether you want to have greater rotation or less rotation. Okay, so it's a physical quantity that describes the twisting effort, okay, or turning effort. It gives the rotating body of an angular acceleration. So what you can see there, okay, listen here carefully. F is equals to ma is related to linear motion. So right now, torque is related to angular acceleration. So basically, this is what we do. Force in linear motion becomes torque in rotational motion. Somehow it looks like J, but it's like that lah. Okay, and then acceleration in linear motion becomes alpha in rotational motion. Later, I will share with you the mass of linear motion is related to moment of inertia in rotational motion. So this is basically the similar version of Newton's second law for linear and rotational motion. Again, force in linear similar or equivalent to the torque in rotation. Mass is equivalent to the moment of inertia. We'll discuss this in a bit later. And acceleration equivalent to angular acceleration. So basically, the way for you to remember the formula is basically the same as how you remember for linear motion. Okay, so you just change the unit there. So for the example, okay, you can have for the boat being tightened or loosened by spanner, and then door being turned about its hinges. So hinges here means the axis of rotation lah. Okay, the fixed part of the door. Okay, or if you have your book with you, okay, there's a book. If there's a book in front of you, book is also another example you can use as rotational motion, because one side of the book is fixed. In order for you to open the book, you need to add some force to open the book lah. Okay, and there should be some distance between the end of the book and also the axis of rotation. So it should be like that. Other than that, you can also find the elbow. Okay, your elbow is also your rotational motion. If you have this, okay, in your body, that's the closest example you can find. Elbow is somehow a fixed point. So if you use your hand up and down like that, so that becomes the rotational motion as well. It's just that the force you exert is the force exerted by the muscle of your body. Okay, so it's azan. Let's take a break for 5 minutes. Okay, so we'll continue right after this. Let me check the chat. Ask me directly what is torque in Malay. Alamak, torque in Malay because I don't know what is torque in Malay. What is torque Understand that I haven't really define what is this equation. I just want to show you that this is an easier way for you to remember for the torque. But actually torque has two formula. Okay, so this is the second one actually. Torque equals to I alpha is the second one, where if you want to use this one, it's related to the acceleration or angular acceleration of the rotating object. So how fast it is rotating, something like that. So the first equation is this actually. Oh, later. Okay, so these are part of examples that you may find for the torques. Okay, you can have something like this when you're pedaling your bicycle. So the gear is actually fixed, okay, or attached with the pedal, and then from the pedal itself, okay, you can see that whether you need to put extra force or just an average force when you're pedaling so that the bicycle is moving. And then if you want to tighten or loosen the bolt, okay, you can use these tools, okay, to make the rotational motion. And then there is also a different where the length of the tools also being a factor. So how far you need to put your hand from the axis of rotation will show you the results of the rotational motion. So if you put or if you exert the force near to the rotation, it is actually very hard for you to rotate the bolt. So in order for you to have easier rotation, you have to do it far from the axis of rotation. Then you will also have greater rotational motion with less force. Okay, so with less hurt. Okay, the force would be the torque will be depends on the force and how far it is from the axis of rotation. So so this is just the analogy just now. Okay, so from F equals to ma, you will see that greater force lead to greater acceleration. So in torque, it means you have to find greater torque for you to have greater angular acceleration. Okay, so basically, if you have more torque, means it's easy to rotate. Okay, so this is the equation related to, let me see the next part. Okay, this is the equation related to the torque generated by force. So basically, listen here carefully. For the torque, it is basically refers or depends on three things. Okay, see this very carefully. The torque equals to Fr sine theta means in order for you to calculate for the torque, you must know what is the force, what is the R, what is the sine theta. So F is the force exerted, R is what you call as distance between the center of rotation or pivot and the point where the force is applied, and the third one, angle between the direction of the force to the radial line. So in this case, okay, what you have is, let's say the pivot is here at O, and then this is where you exert the force. So when you exert the force here, okay, you can see that there is two components. So when you have two components of F, because you see here F comes with a certain angle. So when F comes with certain angle, it means you have to resolve it into Fx and Fy. So Fx is in x-axis, Fy in y-axis, like that. So allow me to use this part. Okay, so let's say this is the plank just now. Okay, you have the axis of rotation right in the middle. So let's say you have the force 1 here. This is the force. Okay, imagine that this is force 1, and okay, you fix the point in the middle. If you exert the force here, this object will start to rotate. How is it rotating? Again, the direction of the rotational motion will be about the axis. So if this object is rotating, you pull it up, this object will rotate that direction. Okay, in other words, it becomes like that.
Anti-clockwise. Yeah.
Okay, it becomes like that. It makes a certain angle like that. Can you see that?
Yes.
Okay, so it will
Yeah.
rotate, and it is what you call as counterclockwise direction. So it means F1 here, if the F is like this, it will rotate counterclockwise. So let's say, okay, kena like erase. Okay, one more time. Okay, so you have this plank again. The axis of rotation is in the middle again, and you exert the force to this direction. Can this object rotate?
Cannot.
Cannot, because it is fixed there, and the force you exert is parallel to the distance of from the axis of rotation. So right now, okay, the equation is torque equals to Fr. You need to know where is the line of the force, and it must be perpendicular to the radius in order for it to rotate. So right now, the force here and the R from the R is should be the distance from axis of rotation. So if the F you exert in the same line with the R, this object will never rotate. Okay, will never rotate. So that means between, okay, back to the question just now. Okay, back to the question just now. You have a force that is coming with a certain angle. So when you have the force coming with certain angle like that, F, so that means this F comes with a certain angle here, means you have two component, Fx and Fy. So between Fx and Fy, which one will make rotation?
Fy.
Fy, because between Fx and Fy, you must find the force that is perpendicular to the R. R is the what you call is distance from axis of rotation. In other books, they will call this as moment arm. Okay, so this is 90 degree to the R, so this will make a rotation. And F here, this is the angle. We know that when the angle near to the x-axis, this will use cos, and y will use sine. So that's why the equation becomes Fr sine theta. Okay, so like that. Or you can name it as F sine theta multiplied with R. Doesn't matter because it's all multiplied anyway. So basically the equation to find torque is Fr. But in order for you to calculate for the torque, make sure that the force must be perpendicular to the R. Okay, perpendicular to the distance to the axis of rotation. So yes, it becomes torque equals to Fr sine theta after that. Okay, so please know that you need to find the force that is perpendicular. So this is basically how you do for the force multiplied with the distance. Okay, for you to use this tool to tighten or loosen the bolt. Okay, so it's like that. So in order for you to have to rotate easily, you must have better torque. So you must have big torque. So in order for you to have big torque, normally you will keep your force and radius away or far from the axis of rotation, because this is your axis of rotation. So if you keep the force greater, then you will have greater torque. If you keep the R greater from the axis of rotation, also will make the torque bigger. So when the torque is higher or bigger, it will be easy to rotate compared to if you just exert the force near to the axis of rotation. You will feel harder to rotate the object. Okay, so that's the use of it. Okay, that's the use of it. And yeah, this thing has been explained. And this is also how you apply to rotate the object. So see how it is done. Okay, from maximum torque to decreasing torque and no torque at all. Okay, so this is how it is done. Okay, if it is perpendicular, you have maximum torque, and then it becomes decreasing, and when it is parallel, you cannot make any rotation anymore.
Miss,
Yes.
why is like the graph for the force towards the hand and not towards the hammer. I mean towards the, what's it called, that one? A spanner, is that a spanner?
The spanner again?
Like
Huh?
for this one, right, the force is calculated from the plank, right? Like the Fx component and the Fy's component.
Okay, this Fx and Fy. Again. Why? The what?
It's calculated from, I mean, the graph is drawn from the object, right? That's,
From the torque. No, the torque that you need to calculate depends on how far the force is exerted from the axis of rotation.
but this graph is drawn on towards like the object we are applying the torque towards it, right?
What graph? I don't see any graph.
I mean like the Fy component and the Fx component.
Fx and Fy, yes.
So this thing is drawn on the object, right?
Yes, in the object, yes.
But in the previous motion video, Miss showed was towards the hand.
Yeah, because no, this is where the hand is pushing the. I mean, pushing the tool lah.
Spanner.
The spanner here. So if you exert the force in perpendicular to the axis of rotation, this is where actually just to show you where the direction of the force. So when the force is exerted perpendicular to the R here, it will give you maximum torque. So it will have decreasing torque if the force is having angle until it becomes parallel, then no more torque there.
This guy's not very good at using a spanner, I see.
Making his head.
So this one is just showing you the variation of the force direction. Okay, not showing you the rotational effect yet. Okay, not
Yes.
showing you,
What's the SI unit for torque?
SI unit for torque, I think.
It's
Dah
Newton
ada ke
meter
tadi?
square, right?
Newton meter
No,
square?
only Newton meter. Only Newton
Newton
meter.
meter.
Okay, because
Newton.
it's referring to FR, then it should be Newton and meter. That's it.
I see.
Okay, torque equals to Newton meter dah. Okay. Alright. Okay, we haven't gone to the example yet. Okay, that will take more time there. So, for the torque motion and effect, okay, it is also just like I said to you, referring to the opening of the door. Okay, so that's why there is a reason why the doorknob is at the end on the other side, not near to the hinge, not in the middle of the hinge, because if you have the force exerted right on the hinge, you will never rotate the door. If you put the doorknob right in the middle, it will be little effect. It will be a little bit hard for you to rotate the door. So the doorknob will be right at the end so that it will give you maximum effect or easier for this door to rotate. Okay, so that's the reason why you have the doorknob at the end of the door. I mean, at the end of the other side, okay, or from the hinge. Okay. And yeah, this is basically what I just explained. Okay, and you also have this, the word moment arm here referring to the R. So instead of just referring the R as radius, it's also referring to how far it is drawn from the axis of rotation. So this is the axis of rotation. For example, this is actually the door, but you see it from the top. Okay, so please have the imagination like that. Okay, so if this is the door and you exit the force like that, more or less, this is the line of the force. And you normally will try to find what is the R that is perpendicular to the line of force exerted. So this is the line. It is 90 degree. Then you will have torque calculated from there. And if you have on C, the force exerted basically in the same line with the R, you will never open the door. Okay, you will never rotate the door like that. Okay, so yeah, just want to show you the other name. Okay, for the R is moment arm. Okay, moment arm. Okay, and this is also how you can see the positive torque and negative torque. These are the two direction. Only two directions related to the rotational motion. You call it as counterclockwise rotation. I normally use as CCW. And clockwise rotation is what we normally use as CW. Please remember, positive torque is CCW, negative torque is CW. Refers to counterclockwise and clockwise direction. Okay, and this one, okay, how do you know whether it makes positive torque or negative torque? So you can see from the force exert here, okay, if you exert the force there, it will make this plank rotating clockwise like that. Okay, refers to the axis of rotation. Okay, this is how you define the direction. If you exert the force here, this thing will go down and rotate about this axis. This is negative. And if you exert the force on this side, this object will go down and refers to the axis of rotation. It becomes counterclockwise. So counterclockwise is positive. This is also what you can find if you play seesaw on the playground, in the playground. Okay, so the seesaw there, you will have one fixed end, one middle point that is fixed, and then you can see that the players will go up and down. So this rotational motion, even though it is not a full rotation, but still you can see this is rotating clockwise or counterclockwise. So you will see the girl here, if she is going down, this is basically refers to clockwise motion. If she's going up, this is referring to counterclockwise direction. So please remember, clockwise is negative, counterclockwise is positive. Okay.
So the greater the distance, the greater the force, or
it's not the greater the force. The greater
Torque.
the distance, the greater the torque. Yes.
Mm.
Okay. So again, your equation is torque equals to Fr. Okay. To make you remember it easily, it becomes Fr sine theta when you need to find the force that is perpendicular to the R. Okay, so this is the formula. Please use it carefully. Sine theta. Okay. All right. Lantok. Okay. Okay, next, let's try example 11 together. This is the first example related to the torque. Okay. I know with all the explanation related to the theory, somehow, okay, the theory is a little bit confusing. So let's try to do it with calculation. Okay. The question comes like this. Okay, let's try to do this together. Let me pick another color. Okay. The question is, the belt of a conveyor wraps around a pulley of 4 centimeter diameter. So you see that you are given with the diameters. As shown, the tension of the upper belt segment is set higher than the lower belt segment. Assuming there is no slip between the pulley, means the rotational motion is smooth. Okay, what is the net torque applied to the pulley? So you know that this question will relate to the equation torque equals to Fr, because tension is a part of force. Okay, so when the tension or any type of force comes into picture, it means you will calculate for the torque. And then you are given with the diameter, which is 4 centimeter. So you know that the first one, okay, let's name this as F1. F1 is exerted towards the right. F2 is also exerted toward the right. And how do you calculate for the net torque? You know that when you have two forces, it means you have two torque. One, rotation because of F1. Because if you don't have F2, F1 will rotate like that. If you don't have F1, F2 will make this rotating that direction. So in other words, they are not cancelling each other because one of the force are bigger. They are not the same. So how do you calculate whether it is rotating clockwise or counterclockwise? Basically, logically, you know lah which direction. But
Look
okay,
at the force.
look at the force. But in order to calculate for it, okay, see this carefully how you calculate. For line of the force of F1, this is the line of force. The distance towards the axis of rotation that is making 90 degree is here. Alamak, okay, make it a straight line there. Okay, so this is where the R and F is 90 degree. Again, why do you always need to keep the 90 degree? That's when your torque is maximum. Okay, that means it is easy for this object to rotate. And then for F2, this is where the R is located. So you see that F and R must be perpendicular. Okay, so how to calculate for the net torque? So summation of torque means you need to add the torque from F1 and the torque from F2. So it should be torque 1 plus torque 2. Okay, see this carefully. And then you know that torque 1 will give clockwise direction. Torque from F2 will give counterclockwise direction. Again, how do you know it is clockwise and counterclockwise? From the force here, make it refer to the axis of rotation. So this is where the force is being exerted. This is where the axis of rotation being put. So from force to the axis of rotation, it is clockwise direction. So this is CW. And then from F2 towards the axis of rotation, this is CCW. So you know that torque 1 is negative. Torque 2 is positive. So why do you have torque 1 in negative here? It's not because torque 2 is greater. It's because of the direction. So I don't want to confuse you here. So please get the idea that plus and minus for the torque is because of the direction. Okay, so from there you put the negative sign. F becomes 30 multiply with the the radius. Here radius should be 0.2 and then okay, proceed with the calculation. You should be getting this answer. So I'm giving you 3 minutes for you to do it and then try to digest the ideas and get the final answers right. Okay. Okay, so proceed, okay, and then continue with the calculation. This is not done yet.
Yeah, everything must be SI unit, so you have to change from cm to
meter. Yes. Yes, what's the question just now?
0.02 kan?
Yes.
0.02. Thank you. Okay, so 02. Okay, my bad there. Sikit lagi. Allah.
So if it's turning,
I really don't understand about the counterclockwise and the clockwise rotation of the apa nama dia tu? Yang bulat tu.
Okay, the disc.
I really don't understand how can the rotation, the direction work.
Okay, first try to remember yang trigonometry. Kalau kita gerak ke kiri, dia akan jadi positive, like from quadrant 1 to quadrant 2, quadrant 3, quadrant 4. So that's counterclockwise. So counterclockwise is positive. And then clockwise, dia akan jadi negative. Macam jam, dia akan negative. So from the first torque, kita tengok yang force 1 30 Newton. So first kita try abaikan dulu yang force 2. So like perpendicularly, so dia akan gerak ke clockwise, right? So dia akan jadi negative. tu yang first torque. And then the second torque kita ambil yang 20 Newton pula. So kita abaikan yang first, dia akan rotate ke counterclockwise. So dia akan jadi positif. So kita kena tahu kalau on torque ni kita tahu direction tu dulu. Then kita boleh applykan ke dalam formula.
Okay,
So, sampai
thank
ni
you,
faham?
Mirza. Okay, thank you. Okay, let me try again with another
Explanation.
what you call another slides. Okay, let me put another slides there. Okay, what is this? Okay, so for the okay, you have the what do you call it, this like this just now. Oh, whatever. Okay, so if you exit, okay, when you want to define the direction of force 1 and force 2, if you refer to force 1, you have to think that force 2 is not there. Imagine that it is not there at that point of moment. Okay, so let's say your axis of rotation in the middle here. Okay, and then if you exert the force there, this is F1. If you exert the force towards that direction, this object will rotate like that. So this rotational motion is basically clockwise direction. This object will rotate towards that rotation. It cannot move, of course, because you already fixed it right in the middle here. So in other words, if you have the object there and then you pull it to the right, this object will rotate clockwise. So I don't know how you need to imagine. If you have anything at all in front of you that is in circular shape, try to do it.
Try buat trigo punya tu. Nanti at least dia orang faham base macam mana direction. Yang quadrant 1, quadrant 2, 3. Itu pun dah boleh buat satu.
I think it's actually the same as this one. Okay.
Ya, memang pun.
And exactly if you have F2, if you fix it in the middle, if you exit as F2 on this side, okay, basically this object, because it is fixed, it cannot move, so it can only go that direction. Okay, like that. So this is counterclockwise direction. So if any of you who can explain better, okay, so try to, I think if you have an object in front of you, that would be the best. Okay, you try to experiment this with any object, maybe a cap bottle, bottle cap or anything, okay, related to the circular shape. You will see the rotation better. Okay, so that's how it should be done. And in order for you to calculate for the net torque, you must add all the torques, but consider the direction as well. If the torque meet is positive, it should be it's counterclockwise, it should be positive. Clockwise, it should be negative. So yeah, that should be it. Okay, let me just try to okay, I cannot clean the board, okay, because it's being discarded yet. Okay, so try to calculate. The answer is there. Okay, if you I want to have the full calculation, because it's a mess here in the slide, so please download the slide and calculate again. All right, and yeah, referring to example 11, I give you another example 12. Okay, right now again, do it one more time, but we are having two forces with angles. So I'm giving you 3 minutes for you to try to calculate for this. Let me give you the answer. Where's the answer? Anyway. Okay. The answer should be 2.46 counterclockwise. So please get this answer. Counterclockwise should be like that. So if you just put this symbol, it is understandable. Okay, you don't even have to put clockwise or counterclockwise, CW or CCW. You just put this symbol, it's already understandable. Ow. Salah. Ini adalah clockwise. Okay, you have two forces both forces comes with angle, then what you need to do? Okay, you can name the first one 8 here as F1, the second one here 10 in the direction. You know that 25 is the distance from axis of rotation for F1. 75 is the distance of axis of rotation from F2. Then next is, because both forces comes with angle, that means you need to have your
F1.
F2y and F2x, and then check again which one will contribute to the rotation. F2 pula. F1x. Okay, so between F1x and F1y, which one will contribute to the rotational motion? And if they contribute to the rotational motion, will it make clockwise motion or counterclockwise motion? And then proceed with the summation of torque. Summation of torque is always plus for CCW minus for CW. So please find the symbol T2. So I'm writing my answer down for you as well at the same time. So F1Y, sorry, this is not the color. Okay, F2Y will make counterclockwise direction. F1y will make clockwise direction towards the axis of rotation. So this is plus and this is minus, and that means tau 2 will be plus, tau 1 will be negative. Yeah, okay, proceed from there. You should be getting the final answers, 2.46 Newton meter. So you need to try to do this. Okay, previously torque has been killing a lot of students, so I don't want that to happen to you this semester. Okay, if you don't understand it today, I can understand, but put your effort more to understand the concept better. Okay.
Miss,
Yes.
what's the difference between moment and torque? I don't get it.
Moment and torque.
Yeah.
Moment is the R, the distance between the force you exert towards the axis of rotation. Torque is how it is rotating.
Miss,
Okay, thank you.
I got 2.464.
Yeah, I think it should be okay.
Thank you.
Miss,
Yes.
how to
Miss.
know the for the direction the clockwise counterclockwise for the final, how to know it's clockwise
Depends
or
on the
counterclockwise?
answer, right?
Depends on the answer, because you already consider the plus and minus. If
Oh.
your final answer is positive, it means
Counterclockwise.
counterclockwise. If the answer is negative, it means clockwise.
Oh, okay. Thank you.
You're welcome. Other question?
The answer is 2.46.
Yes. 2.46, yes, correct. So that should be it. Okay, let me scratch this part a bit. Okay.
Miss,
Yes.
could you like give us an example of an object that has two torques? I don't get it. Macam like pintu kan ada satu je torque kan?
Yeah, I gave to you just now. Seesaw.
Oh, lah. Okay.
Okay, you have that. Seesaw is when you play seesaw, if you play only alone, of course, it won't rotate. Okay, it was just having you will be the axis of rotate. I mean, you will be the one, okay, on the ground. But if you play seesaw with two person, okay, two person playing seesaw, one at the end of one at the right end, one at the left end, then you will see that it is moving up and down like that. So that is part of the rotational motion. Okay, it's not the whole rotational motion, of course, because you don't go, flick backwards like that. So it's just a matter of you will be rotating downward. I mean, you will be moving upward and downward. So going up will be clockwise or counterclockwise based on where you sit, whether at the end or whether on the right or on the left. So when you play seesaw, is basically you have two forces, one on the right, one on the left. Your fulcrum, your point or pivot is actually right in the middle. Okay?
Tapi Miss, yang tadi tu yang apa? Apa nama benda tu? Soalan sebelum ni. Sorry, soalan sebelum ni.
Yang this tu ke?
Conveyor belt.
Yes, kenapa?
Kenapa top part dengan bottom part tu different macam forces macam tu?
Yang itu the design untuk for you to see lah whether the rotational motion make by those forces will make it rotate clockwise or counterclockwise. Those are just an experimental done, okay, to see the rotational motion on the disc itself.
Wait, Miss. So force, so kita tak guna like F to Y, so we just take the force from that is given.
But only part of the force will be contribute to the rotational motion. Means in 10 Newton, not all 10 Newton will do the rotational motion. Only 10 sine 30 will do the rotational motion.
So okay, if I were to use F to Y, so my sine would be 0 lah. So my sine would be sine 90 degree.
Correct.
Okay, patut lah tak dapat asyik guna. Okay, big brain.
Miss,
Okay, yes.
if there were to be two forces spinning in the same direction, how would the Fy component, Fx component be like?
If what?
Both forces were pushing in the same direction.
Both.
So there's no negative and positive. It's both clockwise rotations.
If both clockwise rotation, then the rotation is clockwise. That means no opposing torque there. So it will be rotating.
How will we know if it's both in the same direction?
In the same direction? Okay, let's say it's in the same direction. Okay, ignore this one. Okay, ignore that one. If it's in the same direction, something like this. Okay, something like this. Oh, sorry, it's weird there. Okay, so first of all, I don't think. Okay, this will confuse you. So let's scratch that one. Okay. So what you will have there is, let's say you have one plank like that, and you say that it is moving towards the same direction, right? This is where, let's say, you exert the force on this side. Let's say I put it downward, and on this side, you pull it up. So this will give the rotational motion like that. This will give the rotational motion like that. So in a way, this will rotate counterclockwise direction because no motion opposing the rotational motion anyway. Can you understand that?
Yes.
Okay, I hope. Okay, so again, if there is two force, okay, again, I put it here. You push this down. This one you pull up. Okay, so this will make clockwise direction. This one will also make clockwise direction. So in other words, this object will be rotating in clockwise direction. You don't have any torque that is opposing the clockwise motion. So yeah, the rotational motion is a perfect clockwise motion. Okay.
Excuse me, Miss. If is it possible for the angle to be in words to say, can you pull the question out again? Can you show the question again?
Okay.
Okay. For example, if the 30 degree was on the other side of the y-axis.
At the y-axis.
Yeah.
Here.
Like that. No. On the other side.
Oh, I understand. That means it should be like this. Like that, is it?
Yeah. Is there any difference to the equation?
No, you will just need to find your x-axis and y-axis still.
So we still use like the same 30 degrees, right?
Correct. So if your 30 degrees is here, then your x still use x will still use cos, y will still use sine.
All right, cool.
Okay.
So this will be counterclockwise because going to the left.
Yes.
If the fulcrum is center, like you draw just now, this one, so the force is equal.
If the force equal, then you don't have any rotation.
Yeah. It doesn't mean that at the center it would be balanced. It depends on how much force you exerted or applied.
Okay, I understand. I understand the
Yeah.
question. Let's say if the R, you have force one like this. Okay, this one cannot. Okay, this one cannot because this one will make clockwise direction. So let's change the question into it is okay. This you change to this one. Okay, one force up, the other one also up. So this is F1 and F2. This is F1. So this is R1, this is R2. If your pivot is right in the middle, means R1 is equals to R2. If your force is also equals F1 equals to F2, then that means your net torque is equals to 0. Because this will bring clockwise direction, a counterclockwise direction. This will bring clockwise direction. Both is the same. Plus and minus cancel, then no rotational motion for the system. Okay?
Okay, I see now.
Alright.
It depends on the formula lah, faktor dia pergerakan.
Yeah.
So if not force,
So-
the distance of the pivot. If not that, the angle.
Correct. So basically, please stay true to the formula. Fr sine theta means, like I said in the beginning, if you calculate for the torque, means the three factors you need to see is the angle between F and R, the value of F, and the R itself. Okay, so those are the three factors affecting the rotational motion torque. Okay, and last but not least for today, I want to share with you the Newton's second law of rotation. This is basically the second equation related to the torque. So I told you just now, there are two equations for torque. One is Fr sine theta. The other one is I alpha. So one is related to the force exerted. The other one is related to the acceleration or angular acceleration. So if an object with mass m subjected to a force directed to the object, directed as shown in the figure, okay, you are going to have the acceleration on the object itself. So from the equation you see here, from F equals to mat, F you substitute there, this is F equals to ma, and then you know that AT from the equation that we have just now, okay, AT is equals to R alpha. Okay, AT equals to R alpha. This is tangential acceleration. Multiply with the, AT is equals to a radius multiply with the alpha, angular acceleration. Then you put it in for the AT, you will get mr square multiply with alpha. Then mr square is what you define as moment of inertia. So this is what I say is equivalent to the mass in the linear motion, but in rotational motion, the rotation is depending on the mass and how the mass is rotating related to the axis of rotation. So for I equals to the moment of inertia, okay, so sum of torque is referring to this equation, summation of torque equals to I alpha. I is what you call as moment of inertia defined by mr square for a very small object. So this is what we can do to compare. If in linear motion, okay, linear motion, you will say it is F equals to ma. In rotational motion, torque is equivalent to the force, moment of inertia equivalent to the mass, alpha equivalent to the linear acceleration. And for this small object that is rotating, okay, for small mass on a rotating object, it is defined by I equals to mr square. But this rotating object depends. Okay, the rotating object depends on the shape of the object itself. So it's basically, if you try to rotate a ball and if you try to rotate a book, basically they are different. Okay, they are different. Okay, so how do you know and what are the formula related to the moment of inertia? It's basically, okay, first of all, the moment of inertia is given by the formula, given by the unit kg m square, refers to the equation just now, I equals to mr square. So m gives you kg, r square give you m square. So this is the unit for moment of inertia. Please write this down. And for the simple shapes that you are going to calculate in this semester, these are just basic, okay, five shapes that you can find. Okay, think about an end of length L. So this is basically, if you have pen in front of you, if you rotate the pen right in the middle and if you try to rotate the pen at the end, I mean the axis of rotation is at the end, it's different. Okay, it's different. So the equation for you to find the moment of inertia for various shape rotating is defined by these cases. So this one will be given by the question itself, whether you are calculating for the thin rod where the axis of rotation at the end, or you are calculating for the thin rod that the axis of rotation is in the middle. Okay, you see that the equation is different. And then if you have another disc rotating or cylinder rotating, so disc or cylinder rotating, the radius is like that. This is the axis of rotation line, like that. Okay, so if it is rotating like that, your equation is half mr square. If the object is something like ball rotating, then the equation is another equation, okay, a little bit different. And if you rotate something that is in shape of rectangle, okay, so you will also have a different formula to find the moment of inertia. So in a way, it is depending on the shape itself. Okay, so different shape will have different moment of inertia when it is rotating. So
do we need to remember all this? Like 1 over 3, 1 over 12?
No. That will be given. Don't worry. Okay, this will be given. Okay, this will be given. But you have to know which case it is referring to. So for example, okay, you can try to do this example 13. Okay, for you to check the rotational motion. The answers are already there as well. But I want to share with you example 14 to show that this is the type of question that can be asked. Okay, you see here, a wheel of mass 8 kg and a diameter given is driven by a constant torque 0.5 Newton meter. What is its angular acceleration? Assume that the wheel shape is similar to uniform disc. So in this case, the question already give you that the case is similar to the disc. So that's why you will be using moment of inertia here refers to half mr square. And since I told you just now that torque has two equations, and whether you need to use Fr sine theta or I alpha, it is basically depends on the information given. So right now, the information given is the mass, diameter, and also the torque. You are calculating for angular acceleration. So basically, you cannot use F r sine theta because you don't have the F there. And you don't have also the angle. And how you can calculate for that? Okay, you can use I alpha, but calculate for the I first, which is half mr square. For the disk, you will get 0.36 kgm square. And then you will get torque equals to I alpha. You will get 0.5 divide by 0.36, you will get 1.39 radian per second square. Okay, so in order for you to use the formula, you need to know what type of information given. Okay? Alright. So, last but not least for today, ya Allah, cepatnya masa berlalu. Okay, last but not least for today, it's example 15. I give you 3 minutes for you to do, and the answer are written in red. Okay, so try to find your answer when the question is giving you two types of things that you need to find: net torque and also angular acceleration. So try to do it. Aduh. Kok ia pun nak main? Tunggu jap. Tunggu kelas habis. Okay. So try to do this. Okay. You need to try to do this together with me in the class. I know you can always watch the recording later, but it's not the same feeling. Okay. So rewatch is something you can do later, but doing this together with me in the class is basically your responsibility, okay? Because you have paid for this session, so don't waste it, okay? So uniform solid disk, that should be the hints that the case is similar or referring to a disk case. You are given with the mass, which is 24.3 kg, and the radius is 0.134 meters. So that means this is already the radius, okay? And free to rotate about the frictionless axle. So that means we take that there is no friction opposing the rotation, okay? If you have friction here, it's going to be mind-blowing calculation, okay? You don't want that to happen. So no, we are not going to have friction there, okay? Sabar. I know that. Yes. I know the fields. But since you are mechanical students, you will see this sooner or later in your degree level anyway. So forces of 90 degree and 125 Newton, 90 Newton and 125 Newtons are exerted on the disk like this. So that means you need to know these are the distance from axis of rotation. This is also another distance from the other force. So we did this just now. For 1 to 5, will be giving a clockwise direction. For 90 Newton, it will give a counterclockwise direction. So this will be negative, this will be positive. Calculate carefully. You see there, the answer is negative. Practically, it's because 125 is greater than 90 when the R is the same. So of course, it will be clockwise direction motion. Yeah. Okay, and then proceed with the calculation for the torque. You can write it as this way. K torque equals to I alpha, but you need to calculate for the moment of inertia first. Okay, so moment of inertia means it's moment of inertia. You call it as moment of inertia because it's referring to the rotational motion when the mass is added in. So if for the momentum, right, okay, the mass will show that the object will be harder or easier to stop moving. Then in rotational motion, this moment of inertia will also tells you whether the object will be easy to rotate or harder to rotate. So it's like that. Okay, and your torque equals to I alpha, then refers to the calculation you have made. Then you will get it as negative 9.17 radian per second square. But you can also write, you can just leave it this way and write it clockwise. Okay, write it clockwise like that. You can also write it as 9.17 and put clockwise direction. So it doesn't matter. If you leave it, your answer in negative also correct. If you leave your answer positive but you put clockwise or counterclockwise is also correct. So basically, both answers are accepted. Okay, so just show that you understand about the plus and minus sign.
Miss,
Yes.
what's I?
Moment of inertia.
Yeah, moment of inertia.
Share.
Moment of inertia equals to Mr. Square.
Okay. All right. So
Miss,
yes.
I have confused about the negative and positive symbol.
Okay.
Can you explain?
Again,
The plus and minus direction.
Yeah.
Okay.
clockwise, negative, anti-clockwise, positive. Yeah, together.
So ada ya. Okay. For now,
I mean,
okay. Let
like-
me
Uh-huh,
get
yeah.
this again. Keep. Okay. Let me unshare the screen. Okay, so that you can see me. Can you see me now?
Yes.
Okay.
Yes.
I have this with me. Okay, this is the something
Bullseye.
that you can see where this is rotating. So if you have this object and this is where you put the force, okay, I put the pencil here at the top. If you exit this pencil and then you exit the force towards this direction, okay, this object will rotate this direction. Okay, together there. Again.
Anti-clockwise.
Okay, I don't know because I think what you see is different than mine, so I don't want to put clockwise or anti-clockwise. So you tell me, okay, if this pen is going to this direction, I think I put the what do you call it, the arrow there. Okay, this thing. Okay, how? Okay, let me put another line better. Okay, like that. So if this object is going to that direction, this rotational motion will go that direction. Can you see it now? Together. Okay, so
Yang tak faham tu jawab.
so now it will make either clockwise or counterclockwise direction based on how you exit the force. You try to exit to this direction, this object will rotate because you fix the point in the center. So if you don't have this fixed point, this object will move together there. But right now you have a fixed point in the middle. So if this goes to this direction, this object will rotate like that. Okay, so you try to check again whether it is making clockwise direction or anti-clockwise direction based on the force you exit. So yeah, basically that should be how you need to check the direction, positive or negative. Okay, so yeah, we don't have time to go for chapter 9, but basically we have done with chapter 8 because we are not going to discuss work, energy and power for rotational motion. Okay, and also momentum, but just to share with you, if you need, okay, let's say, okay, please tell your tutors, okay, no questions related to work, energy, power and momentum for rotational motion. Okay, so please tell your tutor that. And let's say you have questions related to work, power and energy and also momentum. Like I said to you, you can just change the symbol from linear to rotation. Okay, so let's do this together. For Newton's second law, you have F equals to ma. F is equivalent to, sorry. Okay, I know.
Just screaming.
Saya lupa. Okay, saya lupa. Wait, is it now?
It's loading. Okay.
Okay, so again, okay, let's say you are needed to discuss about work, energy, power, and momentum. Linear motion and rotational motion is not that much difference anyway. So let's say for the Newton's second law, you have F equals to ma. So like I said to you, torque is equivalent to the force, mass in linear equivalent to the I in rotation, and acceleration equivalent to the angular acceleration. So you just change the symbol there. Work equals to Fs. You know that F equivalent to the torque, then change to the torque. S is displacement. In rotational motion is angular displacement theta. So you just change it to tau theta for the work done. For power, we have previously force multiplied with velocity. So it is the same as torque multiplied with angular speed. It's the same. Kinetic energy is half mv square. Now you just change it to half I omega square. And last but not least, if it is momentum, it is P equals to mv. The symbols for momentum in rotation is L. M equivalent to the moment of inertia. Velocity is equivalent to the angular velocity or angular speed in rotational motion. So basically what you have in linear motion, the exact equation is used in rotation, but the symbol is a little bit different, and the unit also a little bit different, because unit for torque is Newton meter, unit for force is Newton. So basically you need to do the chapter summary for you to use, okay, and for you to see what are the things that you need to focus more on rotational motion. But okay, I think it's safe to say this, okay, these work, power, energy, and momentum will not come up in your final exam. Okay, we will discuss this just briefly, okay, in this chapter, but it won't be asked in your final exam anyway. Okay, so yeah, that's it for chapter 8. When we come back, I will share with you how to use torque in static equilibrium, and also we have another part on chapter 9, which is called elasticity. So please read on chapter 9, and we also need to finish chapter 10 because it's going to be in your test 2 as well, but our test 2 is like 2 weeks, it's like 3 weeks from now, so it's okay. So you just prepare what you can from chapter 6 until chapter 8 that we have done. So yeah, that's all for today. Let me give you the yes,
I have a question.
yes.
You know, since many people are confused with the direction, after that circle explanation, I also got confused. So if you turn to the right, then it's negative. And then the right, when you turn to the left, then it's positive. But right, if we switch those values at negative, positive, does it even matter as long as you keep it in the same direction? As in like, wait, how do you explain it? Like, okay, so if you go to the right, instead of negative, you use positive value. And then the final answer, when you cancel it out, and it's negative value, that means it's to the right lah. As long as you keep the calculation and the answer like the same.
Your plus and minus, right or left, is a little bit messed there, because our direction for rotational motion is not defined by left and right anymore. It's defined by whether the rotation is clockwise or counterclockwise.
Oh yeah, sorry.
Okay. So whether the force is, to the right or to the left, it doesn't matter. You need to check whether the rotational motion is clockwise or counterclockwise. If it is clockwise, then it is negative. It is counterclockwise, it's always positive. You cannot change that.
Yeah.
But if you get confused by it and then you do change it, meaning clockwise is positive and then anti-clockwise is negative.
Basically, for your understanding, if you change that, that will just give you
confusion.
That is depending on your understanding, but you are against the law. You are doing against the law.
You get fined.
Yeah, because if you are if you are in the real world, you cannot change it like that because rotational clockwise is always negative, counterclockwise is always positive. That's it. But if you change that reference, that would be the things that you need to explain. Okay, indeed, why you change that.
At the end, you have to justify your answer. Yang tu yang kena lagi banyak explanation. If you do it like just follow the law ke apa, at least you can just shorten out your justification nanti answer.
So if you're planning to get a PhD, so you can do a research for this.
Yeah. You
Try to do it. But so far, like I said to you, I already explained to you why it is taken as plus and positive and negative. It's just that, I think if you ask in maths as well, normally positive is counterclockwise, negative is clockwise. So if you find any things that can be, you can prove that you can change the reference, you can share with us. Okay, I no problem with that. But so far, as I have completed my studies up to this level, it's always like that.
Okay.
And plus, Nikita, the best way you can actually get this thing in your head, right? It's like, you know that quadrant 1 always starts from the right, right?
Oh, no, I get it. It's just that I was thinking, in forces, like normal forces, if you keep one force in one direction and the answer is negative, wait. The force is pushed to the right and then it's a negative direction, okay? Then
so
the
negative direction means it's clockwise.
Plus, Nikita, if you change it like the one that's supposed to be positive and you change the negative, in the end your calculation you won't know where is actually turning from which direction. You don't know whether which force is going to cancel that force,
It's like you are against the world. People are saying things like this, but you are saying things like that. You understand that actually in your head it's the same thing, but if you tell that to people, it's different. So I understand it might be a little bit difficult for you to take it right now, but try your best to to change it back, okay, to according to the physics law.
So for now,
I'm just trying to understand the concept. I know how to calculate everything. Just
understand.
Concept a bit.
Okay, I know you don't understand it in terms of just the direction. I know you can calculate, no problem. But okay, like I said to you just now, okay, try to do more exercises. Maybe you will be familiar with the direction that we do. Okay, it's the same as how you familiarize yourself with with sine and cos. Which one is cos, which one is sine. So it's basically the same.
Okay.
Okay. I'm not saying that what you understand is wrong, but I hope you try to do more exercises for you to be familiar with the direction. All right?
Yeah.
Okay. It's okay. You can ask question. I'm not mad at all. Seriously. Okay. So if I can answer that, I will try to have question. Before that, all of you please do this scanning for the attendance, and if you don't have any question, you are free to go. Thank you so much. I'll see you again. Okay. Any question? That is angular momentum. You call it momentum in linear. It's angular momentum in rotational.
Angular momentum.
Yes, angular momentum. So if you remember in chemistry, you have, I don't know, you already done this or not, the NMLS. It should be the, have you done that? The spin, magnitude, spin up, spin down. Have you done that? No, in chemistry, not yet.
Again.
Sure.
The electron spin. The electron spin.
Electron configuration.
Where you have electron configuration.
Right.
Half of it up, half of it down. You have
Yeah.
Okay, from there, okay, let me just share with you. What is it? Okay, so let me just share with you that you have this L is basically a little bit in chemistry lah. A little bit in chemistry refers to the same L you have in chemistry. So okay, those siapa yang tak nak confuse tak payah dengar lah Okay, so if you have electron configuration kan, you have the N which is the state, and then you have the L, and then you have the magnitude number, and then you have the spin, right?
Yes.
So this L is the angular momentum for this. For the electron, it's the same as the L in physics. It is called L as well.
Oh wow.
Yes. Okay.
But
So
then
because
Wait,
Yeah,
is it L or is it I?
L is L. It's small L here. Okay, small
Yeah, L is to point out which
It's
subshell it
momentum.
is.
Here, momentum here. It's
Momentum is
angular
written as L?
momentum. Yes, angular momentum is L.
But in what we learn is from the S part where it shows the direction of electron.
That one is just a basic idea of it. You will have to do more atomic level scale, then you will see that's right. Okay, no need. Okay, stretch that part. You will be confused. Okay, so L is the momentum for angular acceleration, angular or rotational motion. Okay. Okay, so that's it. So back to the attendance. Please do the attendance again. Okay, and then if you haven't. Okay, and then I'll stop recording for today. Okay, and then I'll see you again next week for chapter 9. And have a great weekend. Thank you so much. Bye bye.
Miss,
Thank you, Miss. Bye.
Question.
just curious, but like, at any point will we ever learn what's Magnus effect?
Magnus effect.
Thank
no.
you, Miss.
Welcome. Bye bye. For
Why?
Magnus effect, Magnus
So fun.
effect is actually it's fun if you can read about Magnus effect, or there is another name for it. Apa ya? Something about started with V. I cannot remember. What is that V? I cannot remember. Okay, so for the Magnus effect, it's quite tricky to explain why it happens, but it's a physics phenomena. It's a science phenomena that is quite interesting. But
It
you
falls under the law.
won't have the specific calculation in foundation level. Not this time.
Because it's influenced by Bernoulli's law, also, right?
It was about
Influenced by Bernoulli's law. The movement of air speed.
yes, correct. So that one is also referring to how fluid motion. So that fluid motion is in your chapter 12.
Oof.
And because when it happens, it's also spinning at the same time. There are the air resistance, or the fluid effects will be there as well. So you know fluids, right? Fluids is anything flow. It can be air or it can be liquid. So more or less it's related to that.
Because
Okay.
I saw that you were learning rotational motion. I was like, is that going to be Magnus?
Not this time, but you are free to read on it. Okay, at least you can relate to whatever theory or whatever knowledge you have in physics as well.